Hi, this is Barrett Givens, and in this video, I'm going to talk about this very important theorem. This theorem helps us to understand what the open sets are in a topology if all you're given is a basis. So this is something that we're going to do very commonly. I might give you a topology by saying, well, here are the basic open sets. Here are the sets in the basis. Um, what do the general open sets look like? And so this is the theorem that tells you how to do that. If you're given a basis, how do you describe the general open sets? All right. So the theorem says, let T be a topology generated by a basis B. Then a general set A is open in this topology if and only if, for, let me make these bigger, for every little x in capital A, there is a basic open set, capital B in fancy B, such that it's our usual. X is an element of B, which is a subset of A. So it says that if you want to figure out what the open sets are, you have to think about, okay, if I take a set A and I want to know if it's open, I have to check if I can squeeze this B in containing X inside of A. So whenever I have a situation that looks like, here's my set A, and I take a point X, if I can find a new set B that's a nice basic open set that sort of squeezes between X and A like this, then if I can do that for every possible X, then I know that A is an open set. Okay? So I think that I will not prove this theorem right now. I'll leave that for a different video. But for right now, what I'm going to do is I'm going to think about the basics, the basis. I'm going to do an example. Okay, example. Let B be the collection of open balls in R2. So in other words, B is the collection of all sets of the form capital B X epsilon for all possible X's in R2 and all possible epsilons greater than 0. So B just consists of all possible flat circles with a dotted edge around them in R2. Okay? And let's look at some example sets in R2 and try to decide which ones are open, and then see if we can kind of make a hypothesis about which ones are open. So let's say, for example, that I look at something like, let's say I look at the set that goes from -1 to +1 on both axes. So let's say I look at this set. Okay, let's say I look at this set from -1 to +1 with a dotted edge. So not including the edge of that square. Is this set open in the topology generated by the open balls? Is this set open in the topology generated by the open balls? Well, I want to think about my theorem. My theorem says that this set will be open if anytime I take a point in here, can I stick a ball around it that's inside this square? So if I take a point, like right here, can I take a circle? Is there some circle around that point that is inside of the square? I think so. Just look, I'll draw one. There we go. Okay. What about this point? It doesn't even have to be centered at the point. I could draw a circle that looks like this, just happens to have a center at a different spot, but it could be centered at the point. What if I take a point way over in the corner right there? I can just take a little itty bitty circle around it. What if I take a point right here? I can take a little itty bitty circle around it. Is there any point in the square that I couldn't draw a circle around while still staying inside the square? I think no matter what point I take, no matter how close I get, I can always draw a little circle around it. Okay? And so this is open. Okay. What about if I do the same thing, but I'm going to make one of the edges solid. So this set is the same as the previous one, except that the top edge is included. So now let's say that I take a point in the set, like let's say I take a point right there. I can draw a circle around that point. That one's good. Or if I take a point right here, I can draw a circle around that point and stay inside the set. That one's good. What if I take this point right here? What if I take that point right there? If I draw a circle around that point, does the circle stay inside the set? No, part of it sticks out. Okay, maybe I just need to make it smaller. Let me zoom in and make it as small as I can. Well, still part of it sticks outside of the set, right? No matter what, if I'm right on that edge and I draw a circle around a point on that edge, the upper part of the circle is going to stick out, okay? And so this set cannot contain basic open sets around points on the edge. And so this set is not open. Top edge points are a problem. Okay. What if I were to take the points on the x-axis between 0 and 1, but not including 1? So what if I were to take as my set this like line on the x-axis, but not including 0 and 1? Okay, so kind of like an open interval on the first coordinate axis. All right, let's say I take a point right here, just take a random point, and I draw a circle around it. Does that circle stay inside that green set? No, it doesn't. Okay, so this is not open. What if I were to do something like, let's say I were to do something like that. Just some set that's all dotted around its edge, so none of the edge points are included, but it's just all the sort of inside of this funny shape. Okay, and then take a point like right here, draw a circle around it. Take a point here, I can draw a circle around it. Take a point here, I can draw a circle around it. Take a point here, I can draw a circle around it. Right? As long as I'm kind of staying inwards from the edge, I can draw a circle around it. And since the edge isn't included, I can always, any point I take, it's always a little bit away from the edge, right? Since the edge is not included, any point you pick is always a little bit away from the edge. And so I think intuitively what we can say is that sets in R2 are open in this topology if and only if there's sort of like two-dimensional blobs that don't include any edge points. Okay, this is not like the mathematical definition. This is sort of the intuitive definition. All right. And so this theorem kind of tells you how to start from a basis and then work out what the open sets look like. So you start with your basis and then you start thinking about, okay, what kinds of sets can I always get these basic open sets inside of? All right. So that's the big important theorem. And then that's like an example of intuitively how we use that theorem to figure out what the open sets look like. All right. Thank you for listening.